Projection is conversion of a three-dimensional world to a two-dimensional map. It attempts to portray the surface of the Earth on a flat surface, which is known as map that we use every day. And there are many projection methods, and we will introduce the main projection methods, such as cylindrical projection, which is used for UTM and UTM projection, and conical projection, and azimuthal projection, and all other projections. General ideas of projection is like this. You want to project a globe on the surface of either a cylinder or a plane, or a cone. So those are called the cylindrical projection surface, which is shown as the first picture in this slide. And the planar projection surface, which is also called azimuthal projection. And the conical projection surface, which is the third picture. So in conical projection, there are two ways of using the cone. The first way is the easily understandable way, which is you simply include the ball into the cone completely, like the left picture, which is called the tangent method for conical projection. In this method, the cone is tangent with the globe in one circle, which is the upper circle here, shown here. And on this circle, the projection is exactly the same with the real position, because these are touched together. But for all other areas on the globe, it is distorted somehow, either stretched or compressed. And another conic projection is secant projection, where the cone interacts with the globe for a portion. For example, here, between these two circles are the intersection of the cone with the globe. And the globe between these two circles is outside the cone. And the purpose of using secant projection is that within this area, you have much less distortion when you project it on the surface of the cone. For the cylindrical projection, it's the same. You have both tangent projection and the secant projection, where you intersect the cylinder with the globe itself. And also the direction of placing the cylinder is also different. You can have different ways of placing the cylinder. The cylinder can be parallel with the polar system, the two polars, the line connected to the two polars, or it can be orthogonal or perpendicular to the two polars, which is the transverse version. And also it can be any direction due to the user's requirement. And the universal transverse Mercator, which we will talk later, uses this oblique secant cylindrical projection. Basically, the universal transverse Mercator coordinate system tries to get very precise coordinates for every grid on the globe. It separates the globe into many grids, And for each grid, it selects the best direction and the best intersection of cylindrical projection for giving the coordinates of that local area. So using azimuthal projection, you will project the Earth onto a circle on the plane. It's the same way you see the globe, you see the Earth from the space. Basically, the light, because you are so far away from the Earth, when you see the Earth, the light is almost like parallel light everywhere. So if parallel light come to the Earth, and project Earth on a plane, the plane will show such a circle with the projected continents and seas on the surface of the Earth, from the surface of the Earth. And again, you have different directions for azimuthal projection: polar projection, or equatorial projection, or oblique projection, where you choose the direction as you wish. By using various projection methods, you can project the world very, very differently. Some examples are shown in this picture. So between different projection methods, you can expect hundreds of meters or even several miles of offset. For example, in this picture, the blue one is the Lambert conformal conic projection result, and the red curve is the Mercator projection using cylindrical projection. And the green is unprojected latitude and longitude, which is the real line on the 3D globe, the real continental line on the 3D globe. So in this sense, we know that all projections have some kind of distortions from the real 3D space. But the Mercator tends to be better projection with less distortion in this picture. So next we are going to talk the coordinate systems. Some example coordinate systems are global systems and local system. And in global system, the most common coordinate system we're using every day is the latitude, longitude, and height system. And another well-known and widely used system is the Universal Transverse Mercator. It is also the reference for the military grade reference system, which separates the Earth into grids the same way as UTM. And there are, of course, other global systems such as ECEF XYZ and World Geographic Reference System. And also there are a lot of local systems that are designed specifically for a local area so that you get the most precise coordinates for the local area. And there are state plane coordinates, which is the United States designed especially for the United States. And there are universal polar stereographic coordinate system and national grid systems of other countries. And the state plane coordinate system is the US version of national grid system. or not, because the let me correct myself. So the national grid system tries to separate a nation, a country, into a number of grids and use the best coordinating method for every single grid, so that in the end you get the whole national system. But for the state plane coordinates from United States, for every state they have their own coordinate system. So it's not separated evenly into grids. Rather, it is using state-based. It is state-based. The latitude, longitude, and height system is the most commonly used coordinate system today, and it referring the prime meridian and the equator. We know the equator, right? And the prime meridian is a line that across the Greenwich Mean Time line, which is in Great Britain. And the geodetic latitude of a point is the angle from the equatorial plane to the vertical direction of the line, normal to the reference ellipsoid. The geodetic longitude of a point is the angle between the reference plane and the plane passing through the point, both planes being perpendicular to the equator plane. Your distance covered by a degree of longitude decreases as you move toward the poles. This is easy to understand because the circles that is parallel to the equator becomes smaller as you approach the poles. Therefore, for every 1 degree, you cover a shorter distance as you approach the pole. And the geodetic height of a point is the distance from the reference ellipsoid to the point in a directional normal to the ellipsoid. So it's difficult to envision this. So I'm going to give you the picture. So here's the Earth, and this is the equator, and this line is another equator. So the equator is a circle. It is on a plane. That is one reference plane, and another reference plane is the prime meridian, which is another circle that go across the 2 poles and a point in Greenwich, Great Britain. By using these 3 points, 2 poles and this reference point in Greenwich, you get a circle again, and it defines a second reference plane. So what is longitude? The longitude of a point P is this angle from the reference plane that cross the 2 poles and the Greenwich standard point to the point that to the plane that cross the 2 poles and your point P, and you get this angle. So this is your longitude. And latitude is from the equator plane to the plane that let me see. A semi-major axis. It is the angle from the equator plane to this vertical the vertical direction of a line, normal to the reference, normal to the reference ellipsoid. The reference ellipsoid is the surface of the Earth, the surface model of the Earth. So you get this second angle as your latitude. And the height of point P is the distance between point P and the intersection of the line connecting point P to the normal ellipsoid, to the center of the ellipsoid, intersects with the surface of the ellipsoid, which is this point. So this is the height you get for point P. Next, the UTM coordinate system. UTM represents Universal Transverse Mercator, and it is a metric coordinate system, which means that instead of using angle to pinpoint the location of point P, you are using meters to pinpoint point P, to locate point P. UTM divides the world into 6 zones, each being 6 degrees longitude wide. Why 6 degrees? Because this whole circle is 360 degrees, and you have 60 zones. Therefore, each zone is 6 degrees longitude wide. And for latitude, it is designed to be to across 80 degrees from south to 84 degrees to North Pole. The polar regions are excluded from the UTM. The polar regions are using other coordinating systems instead of UTM. The first UTM zone starts at the international date line, which is longitude 180 degree, proceeding eastwards. So this international date line is on the same circle as the reference plane for the latitude, longitude, and height coordinate system, which means that if you recall, that reference plane crossing 2 poles and one standard point in Greenwich, Great Britain, becomes a circle. And on the opposite side of this circle, from the Greenwich standard point, that is the longitude 180 degree. And the first zone starts at this line, proceeding eastward, which is east, the right towards the right, that is the direction east. So you see, this is the 180 degree longitude line, and the first zone is on its right, which is also on its eastward. This is zone 1, 2, 3, 4, and go on. And then you have this circle and come back to 54, 55, 56 till zone 60. So given this information, what is the latitude and longitude to UTM zone transfer for St. Paul, Minnesota, which has 44.9 degrees north and 93.09 degrees west? So you see, these are the degrees. This is the 180 degrees. So zone 1 covers from 180 to 174. Zone 2 covers 174 to 168. And zone 3 covers from 168 to 162, and go on till you have this 93.09, 36 west. The calculation, I'm thinking, maybe the calculation is too much for you to understand, is it? But it's just a basic calculus. So anyway, I will calculate this in class. It should be easy. If you have questions of calculating this zone, you can ask me offline. So these are the UTM grids that we are talking about. And if you calculate the previous UTM zone correctly, you will get zone 15 for St. Paul. UTM has this term false easting and false northing. The false easting is 500 kilometers, and false northing for northern hemisphere is 0 meters, and for southern hemisphere it is 10,000 kilometers. Northing is measured from the equator. That means if you are locating a point in the northern sphere, you will get the distance from that point to the equator as your northing. There's no false northing, or the false northing for the northern hemisphere is 0 meters. But if you have a distance in the southern hemisphere that has a distance from the equator, for example, for 50 kilometers, then what your UTM measure from that point, your UTM measure for that point will be minus 50 kilometers plus 10,000 kilometers. That is the meaning of false northing for southern hemisphere. Easting is measured from the zone line, which means that easting for every zone is from the zone line, rather than referring to a global position. For each single grid of the UTM coordinate system, you have a zone line to refer to measure the easting. And therefore, at equator, you can calculate that the mean and max easting for every grid is 160 kilometer to 834 kilometer. And in the polar region, that is universal polar stereographic grid system, which is different from UTM, because we know that UTM does not include further than 84 degrees north and further than 80 degrees south. So how to calculate this mean and max easting for the equator? We know that the Earth's radius is approximately 6378 kilometers. So we know that the Earth perimeter at the equator is 2 pi r, which give you 40,000 kilometers. So distance for a UTM zone which covers 6 degrees of the Earth's surface will be 40,000 kilometer divided by 360 degrees, and then times 6 degrees, which give you 660 kilometers. And the distance for half of this, so for half the grid, a UTM grid will be 333 kilometers. Since the false easting is 500 kilometers, the easting of the origin is 500 kilometers. That's why at the equator, the mean easting is 160 kilometers to 836 kilometers. UTM coordinate system offers constant distance relationship anywhere on the map. There is no negative numbers or east-west designators. So all the numbers in the UTM system is positive, and it is adapted by military-grade reference system for military use because this grids, the idea of separating the Earth's surface into grids is a good way of giving good and precise coordinates based on projection. We know projection, all the projections have a distortion, and UTM has the least distortion among all the projection systems. UTM transfer to latitude, longitude, and height system. There are a lot of tools to do this. You need to know datum. You need to know the datum and then transfer. So here's an example. This is the geographic coordinates for latitude and longitude. And if you input your UTM coordinates with nothing easting, which are the meters that you get, UTM use meters to position the points, and also give the zone number, and choose the datum to be WGS84 in the case that you get these coordinates from a regular GPS receiver. Then you can get the DMS, DMM, and DDD, which are the hemisphere. Maybe we can try something like this. Okay. Easting is zone 15. Okay, convert. What's the difference? Okay, anyway, we will do this later. Azures wrong value in field zone. Zone sector. Zone. I don't know how to use this yet. Let's try later. Okay, let's go on. Anyways, you want to know that you can transfer the metric system into the angular system. Metric system, universal transverse Mercator. Angular system, latitude, longitude, and height system. So the next coordinate system to introduce is the United States state plane coordinates. The state plane 1983 is based on the North America datum 83. All 50 states are divided into 120 zones, and the local reference system. Individual states have defined their own projection system instead of using a universal projection system. So the conversions can be done with software if you want to convert and get a uniform projection system for the whole United States. You have software to do this work. So this is the state plane coordinates for Minnesota. We are in the south zone. Let me see. Okay. So the coordinate system difference is clearly shown in this picture. For example, as an example, in Texas. So Texas has its own central zone state plane grid, which is the purple grid, and UTM grid is the green lines, and NAD27 latitude longitude grid is the blue lines, the blue dotted lines. We see a lot of difference, and we know that the Texas Central Zone state's plane grid is the most precise way of describing this local area, this Texas Central Zone. So the conclusion of this class is you learned geodesy. 3 methods for geodesy is geodetic datum, coordinate system, and projection. If you want to know the coordinates of a plant, you want to select the coordinates, a coordinate system, either by degrees, which is most commonly used these days, or by meters. For example, using UTM, which is quite precise. And for the coordinating system, it can be based on projection if it's 2D map, or it can be just coordinates on a 3D globe. And if you think about the latitude, longitude, and height system, we decide the angles as latitude, longitude. We decide the angles based on a ball, based on this globe or sphere. So if that one means that it is 3D or it is without projection. But for UTM, it is with projection. You want to remember that the UTM divides the Earth into many grids and do projections based on these local grids and try to avoid a lot of distortion from projection. And in that sense, the UTM needs projection, and the latitude, longitude, and height system does not need projection. However, no matter if the coordinate needs projection or not, no matter if the coordinate system is based on 3D or 2D, it needs a geodetic datum, which is the way to describe the size and shape of Earth. And we know that with different datum, you have different sea level, different average level, and different ways to decide the height on different surfaces, different locations with different surface conditions. So for a coordinating system, it requires this datum. That's why when we try to transfer the UTM to the latitude, longitude, and height system, they ask us to choose if it's based on the NAD 83 or WGS 94 or NAD 27. And GPS reference system uses WGS 84 and NAD 87, which is quite similar in the case of the United States. And the most commonly used coordinate systems include latitude, longitude, and height system, and the Universal Transverse Mercator system, and the state plane coordinate system. Several things to mention. I think everyone will be busy in the week before April 27th. So let's consider field trip week in week April 27 or in week May 4th. And I will see which is a better way to gather information from you and finally decide a day to do the field trip. And the bonus assignment is graded. Please go back and check in the system. And Lab 1 report is due on this Friday. And Lab 2 is on this Friday afternoon. I require that everyone attend this lab exercise because it's easier for you to finish the work in class rather than spend more time off class. So I think it's a time-saving manner if you come to class for the lab exercise. And also I will hand out a feedback survey for the lectures so that I can adjust my lectures or adjust my methods of delivering the knowledge. Okay, thank you.